The next topic what we are going to talk about is the next distribution, which is again treated as one of the probability distribution called as Poisson distribution. As you are all aware of that, the earlier distribution what we discussed was binomial or Bernoulli's distribution, and I said that it is also applicable to the discrete random variable. When we call it as a discrete random variable, when it is countably infinite, right? So probability distribution is completely divided for or completely divided on the basis of two kinds of random variables. One of them is a discrete random variable, other one is a continuous random variable. So initially we are talking about the probability distributions based on the discrete random variable, and later half the remaining distributions will be based on the continuous. So whenever we have the random variable discrete and we say that it is countably infinite, the one of the distribution comes to our mind or into the picture is the Poisson distribution. So apart from the binomial or the Bernoulli's distribution, we will be discussing about the Poisson distribution. A discrete random variable x is said to follow a Poisson distribution with parameters lambda is equal to np, and its density function is given by f of x is equal to probability at x equal to x e to the power minus lambda into lambda to the power x upon x factorial, where x is equal to 0, 1, 2, 3 and so on. So accordingly, here Poisson distribution is nothing but the limiting case for the binomial distribution. Now, when to apply the Poisson distribution? Poisson distribution is to be applied when the number of trials are very, very large and the probability of success is very, very less as compared to the number of trials. Suppose in 1,000 of people, only one person or two persons are dying. So that rate is very, very less. So I can say that compared to number of trials, the probability of success is very, very less. So accordingly, in such cases, we will be applying the Poisson distribution. Now, what is this parameter? This parameter lambda is nothing but mu, which we call it as mean. Mean is mu, which is equal to lambda and given by np. If you remember in the earlier case, of Bernoulli's or binomial distribution also, the mean mu is given by np. So in this case also we will be having mean mu, which is denoted by lambda, and it is calculated as n into p. What is n? N is number of trials. What is p? P is nothing but the probability of success. So this particular lambda will be nothing but the product of n and p, which is always a positive constant. So any probability at random variable x equal to x is to be calculated by e to the power minus lambda into lambda to the power x upon x factorial. How are the values of x moving from? It is moving from 0, 1, 2, 3 and so on. Or the other way of representing this particular probability distribution is the probability distribution of Poisson random variable x representing the number of outcomes occurring in a given time interval or specified region denoted or represented by t is given by or is defined as probability at x equal to x e to the power minus lambda t into lambda t to the power x. Here whatever was the value, that lambda is multiplied with time domain, that is t. So e to the power minus lambda t into lambda t to the power x upon x factorial, where x is moving from 0, 1, 2 and so on. So this is another way of representing the Poisson distribution for calculation of the probability of a random variable x. What is lambda? Lambda is the average number of outcomes per unit time or per unit region. So t denotes the time domain. It is to be calculated in the given time interval or a specified region. And what is lambda? Lambda is the average number of outcomes per unit time or region. So lambda is nothing but mean. So in the question, whenever the language or word used is mean, I can assume that as lambda directly, which will be required for the calculation. See, x is nothing but the value at which you will be calculating the probability. lambda will be provided, or you may calculate the lambda by obtaining or observation of number of trials and the probability of the success. With this, E is already a defined function. E is something 2 point certain values up to decimal places in the calculator. When you do the calculation, E is by default to be taken. So all such values are known. Probability for a random variable X will be calculated as per the requirement. We get the simplification. This is very important note. This distribution is mostly used when number of trials n is large and probability of success p is negligible. Means binomial distribution is approximated to Poisson distribution. So this is what we calculate or when we apply the Poisson distribution. See, after learning all kinds of distribution, we have to identify that depending on the nature of the example, which probability distribution will be applied as per the given data or the situation. Now, similarly, we have the probabilities for the we have the probability distribution and the properties for the Poisson distribution. So, f of x is equal to probability at x equal to x, which is given by e to the power minus lambda into lambda to the power x upon x factorial. The mean of random variable x is given by mu, which is lambda, and which is equal to n into p. Just now we saw lambda is nothing but the mean or the average taken as n into p, number of trials into probability of success. The variance is given by sigma square, which is simply equal to lambda. The standard deviation will be given by positive square root of variance. So sigma is equal to under root of lambda. That is what the standard deviation is. The moment generating function for this probability distribution or the random variable x, which is distributed by Poisson, it is mx of t. The moment generating function is mx of t, which is e to the power lambda into e to the power t minus 1. The characteristic function is phi of w, which is phi x of w, also replacing t by iw in moment generating function. So e to the power lambda into e to the power t minus 1. It is e to the power lambda into e to the power iw minus 1. This is what the characteristic function is. Coefficient of skewness is alpha 3, which is 1 upon under root of lambda, and coefficient of kurtosis, that is lambda alpha 4, which is 3 plus 1 by lambda. Coefficient of kurtosis is alpha 4, which is 3 plus 1 upon lambda. So these are certain properties or the parameters related to the Poisson distribution, which may sometimes help us to get the values directly as demanded in the expected question, right? So this is what we need to keep in mind. The variance, standard deviation, and moment generating function, once those are obtained, we can easily get the characteristic function. So mean lambda is equal to n into p, variance sigma square is lambda, standard deviation is under root of lambda. Now, what can be the examples in which we can find or observe the Poisson variate? Poisson variate means the random variable will be distributed in the form of Poisson distribution. The number of telephone calls received at a particular telephone exchange in a time interval t. Such kind of example can be a case of the Poisson variate or the Poisson distribution. The number of defective articles in a box of 200 units. I told that in a large quantity, when some of the very less amount or negligible amount is either a failure or the success, it can be approximated to the Poisson distribution. The number of deaths due to accidents in a month on a national highway. This can also be the situation where we can uh, compile it to or conclude it to the Poisson variate. The number of breakdowns of a printing machine in a day. The number of alpha particles emitted by a radioactive source in a time interval t. So all such cases come under the case of Poisson distribution, or all such situations come under the case of the Poisson distribution. So telephone calls, very less telephone calls are received if you consider a simple time interval. Also, daily there are no such deaths happening on the national highway. So if you cumulative try to find out the data that in a month how many road accidents are happening and how many deaths are occurring due to that number of accidents, it will be very very less. So as per the traffic which is flowing on the national highway, the corresponding accidents or the deaths are very very less in a month if you see on a national highway. So printing machine, we have to get the output daily. So printing machine has to work in a good condition. So there will be very less incidences, the number of breakdowns the printing machine will have in a day. So all such cases can be approximated to the Poisson distribution. So I hope it is very much clear to everybody.